Welcome to the UGC lecture series. This is the EPG Pathashala lecture series on the subject of computer science, and we are talking about the paper data structures. In this particular module, we will be discussing the implementation of the Queue ADT. So, let us look at who is responsible for the development of this module. These are the people responsible for creating this module and reviewing this module. Now, let us look at the learning objectives of this module. They are the following. It is to discuss the requirements of the implementation of queues. What are the requirements for us to implement queues? Then we talk about the array implementation of queues. There is something interesting here, we will talk about it as we come along, and then we talk about the implementation of queues using circular arrays, and then we will talk about the linked list implementation of queues. Basically, this chapter is about the implementation of queues. So, some of the keywords here are array, circular array and the linked list implementation. Now, let us go to the implementation issues. As I said, first we are looking at what are the requirements of the implementation of a queue. So, first what do we need to implement a queue, in other words? So, we need a data structure, a container to hold the elements of the queue obviously, and then we need something to indicate the front of the queue, and then something to indicate the end of the queue, or the terminology called rear of the queue. So, these are the three requirements that we have to implement a queue. There are two types of implementation using arrays. One is called linear array based implementation and the other is a circular array based implementation. Why we are going for that, we will discuss. Then linked list implementation of the queue we are going to look at, and then you can have a linked list implementation using two external references, that is a reference to the front and a reference to the rear, or a back or rear, or you can have a circular list implementation with only one external reference. That is also possible as far as the queue is concerned. So, these are the basic implementations of the queue, array and linked list. In both we are looking at circular array, circular type of implementation, circular array and circular linked list. Okay. And of course, here in the circular linked list you have only one reference, that is a reference to the back. So, let us look at the first, the array implementation of a queue. So, this is the first approach. There are different approaches in which you can do array implementation of the queue, of what you are going to store, those type of things. So, let us look at that. So, use an array in which the index 0 represents one end of the queue, and here we are taking it as the front of the queue. So, the index of the array 0 is indicating the front of the queue. The integer value rear represents the next open slot in the array. That means, it is not actually pointing to the last element in the queue, but it is pointing to the next open slot in the queue. In this way, when you approach the implementation, what you will have is the rear will give you the number of elements in the queue, because of the 0 starting of the array, of course. So, what is the challenge in this approach is what we also will be discussing as we go along. Okay. So, let us look at an array implementation of a queue. So, this is a queue containing 4 elements. Just let us look at a queue containing 4 elements. So, you have a queue and you have a rear, a pointer to your rear. Remember, front I do not need a pointer, because it is always pointing to the index 0. So, this is the first element. So, the rear will increase. Rear always points one position after the last element of the queue. Here there is only first and last is one element. Then you have the second element. So, that time rear will become what? 2. Then you have the third element, at that point rear will become 3, and then you have the fourth element, at which point the rear will become 4. So, now you have 4 and the rear value will give you the number of elements in the queue also. So, 0, 1, 2, 3 are the positions in the, or the locations in the array which hold the 4 elements of the queue. So, this is a simple queue containing 4 elements. Okay. So, now let us go to the insertion into a queue. So, remember we have discussed in the last module that the insertion, there is no where to insert, you always have to insert at the rear of the queue. That is the definition of the queue, ADT and queue. So, we want to insert the element shown there to the array location given by the rear, okay, and then the rear has to be incremented. This is the basic position that we have to do. So, what do? We first insert that element to the position currently pointed to by rear, and then we will increment rear. So, when we increment rear, this becomes 5. So, this gives the number of elements in the queue as well as and then of course, the rear has been incremented. So, that has to be shown. So, these are the 3 steps, that is you insert the element at the old rear position and then increment rear, and that is what is shown here. So, now rear points to 5. So, this is a simple insertion of element into the queue. Now, let us talk about the removal of an element from the queue. Now, actually I have shown you that element to be removed. I do not have to show you the element, because the only element that can be deleted from the queue is the element at the front of the queue. That is the definition of the queue. So, there is no question of remove or delete or dequeue, because that is the element that is at the front of the queue. So, now remember, now the current position of the queue is that the rear is pointing to 4, 4 also gives the number of elements in the queue, and I want to delete. When I say delete, remove or dequeue, it means that only the front element at 0th index can be removed. So, that is removed. Now, the deletion operation or the removal operation is not complete. Why? Because we have to shift the element. This is typical to an array implementation, you have to shift the element. So, that is what we will do. So, we will shift this, we will shift this, we will shift this, and what else we have left to do? We have to change the value of rear to point to the next the current open slot after the end of the thing. So, rear becomes rear minus 1, and rear now points to 3, and the value of rear changes there also. So, this gives the total number of elements in the queue. This is the steps in the removal of an element or the deletion of an element from a queue. So, you will see what is the problem here. The problem here is that once you do always it is deletion from the front. So, you have to shift elements into to occupy those positions as many times as there are the size of the queue. So, suppose I have 100 elements, and if I delete an element, the only element I can delete is the element at the 0th location. I have to shift all the remaining 99 elements one position to the left. So, this is a problem with the issue associated with the linear array implementation of a queue. Okay. Now, before we go to other implementations, let us look at the typical queue operations that you have. So, the queue operations are create a queue. If you look at the operations that has to do with any ADT, we have up to the point now we have looked at list, we have looked at stack, and this is the third one we are looking at, all linear data structures queue. All of them have similar type of operations. So, we have create queue, we have enqueue, that is this is a term that is used for insertion of a queue, just like you have push for the stack, we have enqueue for the queue. So, you have a queue and an item type item that you want to insert. Then you have dequeue. Dequeue you do not have to tell which item, because you can always delete only from the front. So, you just have to say the queue from which you want to delete. Then queue front, this is similar to top. So, queue front will just give you what is the element at the front of the queue without removing the element. So, the status of the queue remains the same. Queue rear, what is queue rear? Queue rear just gives you the element, because you have at the rear of the queue, because you have 2 access point, you can now access the first element in the queue and the last element in the queue. So, that is the queue rear, and then you have IsFull, this is typical operations for array. So, you just say is the queue full, okay. It is not valid when you have a linked list implementation. Then is empty is valid all the time. So, is the queue empty, are there elements in the queue. Okay. Destroy queue means all the elements of the queue will be deleted or removed. So, these are some of the typical operations. As you have seen from all the modules that we have seen up to now, some of these operations are very, very common: creation, insertion, deletion, though the names are slightly different, accessing elements. Here there are 2 access, because you have 2 access points. Is full, not defined exactly, not necessary if you have a linked list implementation. Is empty, always there. Destroy. So, these are typical operations of ADT, we have defined it in terms of queue. Now, let us look at the Queue ADT. So, here you have the array, you have the 0th element, you have an item, and you have a capacity. So, the front is pointing, always points to the front of the queue, rear points to the rear of the queue, and in case you want, you can give size as the number of elements in the queue. Now, let us create a queue. So, this is a constructor of a queue or the creation of a queue. So, you have to allocate a queue array queue to the queue, and you have to, now this is last we spoke in stacks, again here initial size of the queue is defined beforehand, that means it is static. the size is statically defined, and so you are saying max size. And of course, you can only put elements up from 0 to max minus 1 because it is starting at 0. By now you should understand, you have understood that indexing issue. So, initially front and rear are set to null or 0 in this case, and the size is also 0. Null here we do not say null because it is an array. So, it is both 0 to indicate that the queue is empty. Now, this is the Enqueue or the insertion into a queue. So, first thing you have to do, especially in a queue implementation, is you have to check whether is full. This is when you are implementing it using an array, you check if it is full, and then you give a you signal a queue full condition or a queue full exception. Then what you have to do? You have, I mean, how will you know it is full? If rear is equal to max minus 1, it is full. So, that is how you check for is full. Either you could call the function called is full, or you can check rear is equal to max minus 1. Then what do you do? Now, this is the queue before the Enqueue operation. So, look at this, you have how many elements in the queue? Have 3 elements in the queue. The front is pointing to 0 and the rear is pointing to one position or one location after the end of the queue. So, it is pointing to 3. This is the initial position before the Enqueue operation happens. Now, front does not change. Okay. You put queue, that means it is not full, that is where the else comes. You put queue rear is equal to the data, but that is it is an empty location. So, now Q3 gets 77, okay. And then what you have to do? You have to increment rear. So, now rear points to 4 or rear is equal to rear plus 1, that is 4. So, this completes the Enqueue operation. If you have a separate size, you have to increment that also. You can have a separate operation called size of the queue if you want, but whenever we add elements using linear array, we always add from left to right. So, you keep on adding from left to right till you reach max minus 1. So, the number of the elements in the queue is rear minus front. There is a reason why we are talking about this here, we will come to that as we go along. So, the number of elements in the queue is rear minus front. Okay. Now, let us go to the dequeue operation. So, here we delete and return the element from the front of the queue. There is no question of deleting from anywhere else. This operation, as far as the queue is concerned, is called the dequeue. So, if the queue is empty, you print an error information. In this case, the return value will be useless. So, you cannot return a value, and you have to increment front because you have removed from the front. Okay. So, let us look at the dequeue operation. So, here you have the rear. Here we have looked at a different definition of rear, where rear is pointing to the last element. So, you have to check whether it is empty. When is it empty? When front is equal to rear. Why we will talk about this? Here we are assuming that the implementation uses rear to point to the actual element, last element. Okay, that is the difference we have here. So, it is not empty, you just give queue front, and so here we will return 67 and then make front equal to front minus 1. So, here front becomes 1, okay, in this case. Now, we will look at the operations queue front and queue rear. Remember, both in queue front and queue rear, the state of the queue or the elements in the queue do not change, we just access the queue. So, queue front is return the front element of the queue. Unlike dequeue, this function does not remove the front element. Similarly, queue rear, what it does, it returns the rear element of the queue. That is why we are saying that rear is now pointing to the actual element. You can do it either way, the implementation is how we do it. So, you can use it either way as long as the interface outside to the ADT is the same. So, unlike dequeue, this operation, this function does not remove any element, it does not remove or it does not insert also. So, next is IsFull. How do you check IsFull? The IsFull is the queue signal when rear is equal to max size minus 1. How at this point many items, now this is the issue that we are going to talk about. We are just checking whether rear is equal to max size minus 1. So, I can, how at this point many items of the queue could have been removed. So, the queue is not full. What we mean by this is the capacity of the array has not been used. That is the meaning of queue is not full. So, that means this is a important activity that we are looking at, and this is why we go to the next type of implementation. We will discuss that as we go. So, now we are going to look at a series of insertion and deletions to explain to you how, in spite of the rear pointing to max size minus 1 and signaling a IsFull condition, the actual array is not fully occupied and the queue is not full. So, this what we are going to explain with this small series of operations when we are doing. So, just for your understanding, assume that the red color indicates the front value, the blue color indicates the rear value. We also have a yellow block at different times, which will tell you that front is equal to rear. At that point both are pointing to the same location. Okay. Now, let us assume that initially front is equal to 0, rear is equal to 0, that is why I have put that yellow block there. This is the first empty queue. Now, I have a add 45. So, when add 45 happens, front does not change, but rear becomes rear plus 1. So, rear now points to 1, shown by the blue color. Now, the next operation we are doing is add 67. So, what happens? Rear becomes 2 as shown and front remains at 0. So, that is there, red shows you the front value, and so front is 0, rear is 2. Now, I do a delete. So, when I do a delete, the front gets incremented. Okay. So, now what happens? Front is pointing to 1, deletion has happened, of course, you look at the previous one 45, now that has been deleted. So, front is pointing to 1, rear is still at 2. Now, again I do a deletion. When I do a deletion, what happens? Front becomes 2, rear becomes 2, that is why you have that yellow, both are pointing to the same location or having the same location. Now, we will again continue the operation. Now, remember, full signal only when rear is equal to, in our case, rear is equal to max minus 1, max capacity is 6. So, max minus 1 5. So, when rear is 5, we will get a signal. So, as of now we have not got a signal full condition. Now, I add 59. So, when I add 59, what happens? Any addition, rear is incremented, any deletion, front is incremented, that is our policy. So, now red is 2 and rear is 3 because of the increment. Then again I do an increment. So, now what happens? Rear points to 4 and front points to 2. Then I have front deletion. So, front points to 3 and rear points to 4, no change. Now, I have again done a deletion. So, both are pointing to 4. Now, what happens? I add 10. At this point rear becomes 5, and according to my condition, what am I signaling? I am signaling that the queue is full, because rear is equal to max minus 1. So, what happens? Since rear is equal to max minus 1, it is a queue full condition, though the queue contains only one element, as you can see, it contains only 10, okay, one element, but it can actually accommodate 4 more elements, okay, because front is being incremented and moving towards the rear, that is why we have this problem. So, this is the problem that we tried to solve using circular arrays. I will just repeat this. What we have done is, we are just showing you a series of operations where on continuous call for series of operation add and delete, we are reaching a condition where rear is signaled full because of max minus 1, rear becomes max minus 1, but at that point of time front is not 0. If front was 0, the queue is full, but front has also been incremented because of the deletion, and so you can end up having only one element in the queue, but still the queue being signaled as full. So, to avoid this, we use what are called circular arrays. This is one of the important differences in how a queue is implemented, and because of the definition of the queue, which is different from other ADTs and data structures. So, now let us again look at the Queue ADT. So, now before we go, we run out of space. So, one way of doing that is, that is the problem we had, we will use circular array, but before that you keep the front always at 0 by shifting the elements, which we did initially when we were just talking about that. But that means every time you do an deletion, you have to keep shifting, which is a very costly operation and it is inefficient. So, what we do? We use what is called a circular queue or circular array to represent a queue, both are similarly used. So, you wrap around and use a length variable to keep track of the queue length. So, you do a wrap around. What it means is, this is a linear array. Now, when I reach a full, I go back here and continue here. So, that is what is called as wrap. We will see it more in detail. So, if front not at index 0, no need to shift elements. So, circular array is an array that loops around on itself. Okay. So, the last index is thought to precede index 0. So, what do you do? If you have whatever index max minus 1 will precede 0. So, there is it is not stopped at that point. So, in an array whose index is n, the location before index 0 is index n and the location after index n is index 0. Okay. So, this is the way we do. So, before index 0 you have index n, after index n you have index 0. So, that is how we do the wraparound. But here the problem is we need to keep, in the previous case front was always pointing to 0, but here we need to keep track of where the front as well as the rear of the queue is at any given time. So, that is the only problem here, that we have to keep track of. Previously we had to keep track of rear, front was always at 0, now that is no longer true. So, if front not as index 0, there is no need to shift elements. So, circular array is an array that loops around, that we have already seen. Okay. Now, what are the implementation issues? Implement the queue in a circular structure as we told. How do we know if a queue is full or empty? That is one problem. So, you have to initialize front and rear and we have to test for full or empty queue. So, that is the issue that we have to do. So, use array of size n in a circular fashion. If you see the top diagram is a normal configuration of a linear array representing a queue. The second one is a wraparound configuration. So, you have 0 to rear and the front is coming in front because it is wrapping around. Okay. So, two variables keep track of the front and rear, f is the index of the front element as before and r is the index immediately past the rear element. So, it is not pointing to the rear element, it is pointing one after the rear element. The array location r is kept empty. This is kept empty to indicate that the difference between the full and the empty condition. We will explain that as we go along. So, look at this. Here we have an empty queue. This is we are just depicted using a circular array. So, initially front is equal to 0, rear is equal to 0, that is an empty queue. We have just taken 0 to 5 and then here we have input 3 elements at 1, 2 and 3. So, front is pointing to 0 and rear is pointing to 3 in this case. Okay. So, increment front and then put the element there. Now, this is a full queue. When the full queue is there, what happens? The full can both are full queues. So, here you have 0 and 5 and here you have 3 and 5. So, the difference is only 1 between the two, here 0, I mean 1 in the sense modular 1. Okay, we will come to that later. So, full condition is when there is a difference between rear and full of 1, but that difference is not actual numerical difference, is a modular difference. We will see. This is the circular array implementation. When an element is enqueued, the value of rear is incremented, okay, but it must take into account the need to loop back to index 0. So, that increment means looping back to 0 also. Rear is equal to rear plus 1 q dot length. So, that is how we do the modulus operation. Can this array implementation also reach capacity? Yes, it can, but it can reach capacity only when all but one of the locations is occupied, not like previously. So, suppose I have the array capacity which can hold 5 elements. Previously, even if only one element was there, I had a queue full condition. Here at least 4 elements should be there. The implement depends on the implementation, 4 elements it will probably give you a array full conditions. So, the modified queue operations with circular queue. So, you have algorithm Enqueue, you are here we are assuming we are putting an object O. So, size is equal to n minus 1, then throw full queue, else q rear is equal to 0, rear is equal to rear plus 1 mod n. Okay. Is empty, you check, throw the condition, otherwise f is equal to f plus 1 mod n. So, the only difference we are doing is we are doing a mod operation. Now, we will go to the queue implementation using a linked list. So, here up to now we have looked at array implementation, we did slightly different methods of implementation. One, we kept the rear pointing one position after the last element, sometimes we kept the rear as pointing to the last element. Front also we did in the circular array, what did we do? We kept the front pointing to one position and we started inserting the elements in front plus 1. So, you can, that depends on the implementation. Now, we go to linked list. Internally the queue is represented as a linked list of nodes with each node containing a data element, just like any linked list implementation. But however, we need 2 pointers for the linked list. One is a pointer to the beginning of the linked list called the front of the queue and a pointer to the end of the linked list called the rear of the queue. We will also have, if you need, but we will also have a count of the number of items in the queue. So, this is the linked list implementation, a queue containing 4 elements. So, here we have the linked list. Now, you want to insert an element, so a queue containing 4 elements and then we want to add. So, the new element is added in the node at the end of the list and the rear points to the new node and count is incremented. So, here you create a new node as before in any link, this is the new node, and then you make the last rear point to the new node, and then you have to change the value of count and you have to change the value of rear to point to this node. Previously it was pointing to the previous node. So, this is the implementation of the queue. So, this is the queue after adding the element. Now, after a dequeue operation, what will happen? We do not have to say which element to delete, that is obviously only the front element. So, now you have front pointing to the front element. So, what do you have to do? You have to remove that element and make front point to the next element and decrement the count to 3. So, that is the queue after a dequeue operation. Now, let us look at an ADT list implementation of a queue. As before, even during stacks, we try to use an ADT inside a stack implementation. Similarly, we are trying to use an ADT inside a queue implementation. So, if the item in position 1 of an ADT list represents the front of the queue, the list implementation can be used. So, what do you Dequeue is equal to list dot remove 1, no problem, because you have the 1, get front queue front a list dot retrieve 1 queue front. So, that is the first element. Enqueue new item a list. Now, here the problem is you have to have an element defined as get length, because you have to go to get length plus 1 and only there you can input the element. So, the list ADT here should have the following operations. What all operations? Remove operation, retrieve operation, get length operation, then only you can do this implementation. Now, let us look at an analysis of the different queue operations. The linked implementation of queue does not suffer because of the need to operate on both ends of the queue. You can operate on both ends, it does not suffer because of that. Enqueue operation 0 1 for linked implementation, 0 n for circular array implementation if need to expand the capacity, or 0 1 otherwise. So, that is the. What about non-circular array implementation? That takes a lot of time, because you have to shift the elements every time you do an implementation. Dequeue operation 1 for linked list, 1 for circular array, 0 n for non-circular array implementation. So, that is the dequeue operation. So, enqueue operation is 0 1 for linked, 0 n for circular array if you want to expand, or 0 1 otherwise, but non-circular array implementation problem. Here again dequeue 1 for linked list, 1 for circular array, but 0 n for non-circular. So, both cases 0 n, because you have to do appropriate shifting. So, what have we covered in this particular module? We have discussed the requirements of the implementation of queues. What was special here is we needed 2 pointers, okay, or 2 access points to the queue. So, that was different. Otherwise, you have a data structure containing the elements, and then we discussed the array implementation of queue, the linear array, and we said how the shifting has to happen. If you want to maintain the front at 0, if you do not maintain the front at 0, then we had a problem of capacity full being signaled even if there is only one element, but the rear has reached the last position, because the rear keeps shifting to the right and the front also keeps shifting to the right. Explain the need for circular array implementation of queues. So, here we looked at, we took a simulation, we did a series of operation where the front was shifting and the rear was also shifting, and we found that a queue full signal, though it contained only one element, the capacity was actually 4 or 5. So, that we explained. So, we said that that was the motivation for going for circular array implementation of queues. Circular array implementation of queues only is the viewpoint that you have a mod increment operation, that is the basic difference, otherwise it is the same, but the concept has it is that is wrap around. So, the last element points to the is succeeded by the 0th element, the 0th element is preceded by the nth element. So, that is what, and we outlined the linked list implementation. We also talked about the implementation of queues using a list, but then we needed that get length operator to be part of the ADT list if we wanted to do this implementation. So, with this we have completed the implementation of queues. The next module we will be discussing some applications of queues. Thank you.